Okay, awesome. So let's go ahead and get started now, and more people may trickle in as in the first few minutes of the talk. So welcome everybody to Frontiers 3. This is our third Frontiers talk and our last Frontiers talk for 2024. Frontiers is the series where we invite researchers who are working on cutting edge work to discuss some of the progress that they've made and some of the very interesting things that they're doing generally in the area of intelligent systems. Today, our speaker will be Karan Taneja, a Ph.D. student at Georgia Tech. He works under the guidance of Professor Ashok Goel, who's the director of the Design and Intelligence Lab and the National AI Institute for Adult Learning and Online Education, also known as AI-ALOE. His research focuses on AI tools for education. Today, we're going to hear a little bit about knowledge-based intelligent systems, and we are very honored to have you here. So if you would please, Karan, take it away.
Thank you, Sid. Thank you for that introduction. My name is Karan Taneja, and yeah, I'm a fourth year PhD student. I'll be talking about building multimodal document-grounded LLM agents for conversational AI in education. And I want to acknowledge all my collaborators, especially Professor Ashok Goel, who's been guiding me for 4 years. So I'll begin by talking about just some basics of conversational AI. And for example, if a human comes and asks, "How's the weather in New York today?" and AI gives an answer, we'll just call it question answering because it's a question and it's an answer. But if a human can ask follow-up questions and the agent can understand them in the context of the previous conversation, then we call it conversational AI. And these conversations are grounded in essentially the context of the past chatting. And for these particular queries, it's probably doing some search online. So we'll call that system search augmented or retrieval augmented or document grounded. Further, if I ask, will it be a bad idea to visit Times Square tomorrow based on this chat? And AI comes up with an answer which also has an image. Maybe in this case, it shows like what to expect when it's raining in Times Square. Then it has this image understanding, and it can basically retrieve those images and use them in the chat, right? So I'll call it a multimodal system with search or retrieval or document grounding. So how can conversational AI be helpful in education? So one example, I think from where it started in our lab is classroom management. So a student could ask about course logistics, like when is a project due, what are the topics, and the AI can answer that based on what it knows about the course. It can also be used for a more personalized learning support. So a student can come and ask questions about the course content, like how to solve linear equations with two variables, and the AI could guide the student through a problem. It can also be used in more complex settings, such as in learning by teaching, where let's say we ask the student to teach AI about photosynthesis, and then AI is going to create questions out of the responses and probe them to go deeper into the concepts. So if a student is not able to answer a question, they'll maybe go back to some course content and try to get that answer. So they're learning by teaching the AI. There are some other applications like AI can be used for teacher assistance, so to create questions for exam reviews or just content summaries. They can also be used in classroom forum moderation. So AI could provide useful information and conversations happening on PRs or whatever, and then guide student discussions. And they can also be used as tutoring systems. So sometimes tutors are very rule-based systems, but a conversational AI can provide a natural language interface to those very structured pre-designed lessons. So now I want to talk about some education-specific needs when we use AI or any other technology actually in education, right? So first need we have is that the technology should be personalized to student needs. And by that, I mean the technology should understand the learning gaps, the problems in their like mental models of concepts and try to fulfill them. So based on those learning gaps, it should be responsive and provide instruction that fills those learning gaps, right? And obviously, we expect all these technologies to provide immediate feedback because that's like the holy grail of kind of personalized learning. And finally, some people also talk about like identifying learning styles for students to give them personalized content, but that research is very questionable, and learning styles may not exist based on what we know so far. Um, what another thing we need is just measurable impact. So we want to make sure that every technology we use can actually bring some difference to students' time or performance. By time, I mean the time spent in learning content. So that can be measured through assessments, and it could also be that a student gets the same score, but they learn more efficiently. So they just improve by reducing the time. Also, it could mean that a student feels higher learning satisfaction. So there's these theories of how course should be organized and what all factors play a role in learner satisfaction. And we could see a technology bringing impact to different parts of these like course structures. It could also bring impact in the social interactions, which I'll talk about later. And finally, we want to also know if this AI or whatever technology we're using is bringing student content that is something that they can understand with assistance, right? So there are things learners can do, there are things learners can do with assistance, and there are things they can't do. And so the idea is to kind of expand the zone of uh, uh, things that learners can do, and the technology should operate within this nice space in between where learners can do things with the systems. Uh, Now, I think the remaining needs I'm going to talk about are more generic to also to other technologies. So one is we want correctness. The information should be grounded in instructor-approved course materials. We also want consistent quality answers to questions. Um, Also, when it comes to when things go wrong, we want to know who is accountable, right? Is that if an AI system gives a wrong deadline, is student going to be penalized for it, or is the will the teacher have to change the deadline, or somehow AI is going to be accountable? So those things have to be clear in the classroom. And then finally, there's no room for any unsafe conversation like violence, self-harm, hate, sexual, etc. Another thing I think which is more specific to education is we want to integrate most technologies with existing infrastructure. And the reason is that technologies move fast. We know that, but education moves slow. And I think we have seen it time and time again that it takes a lot of time to get anything into a formal education system. So disruption, I personally believe, is almost never the answer in education. It's always about integrating the new technologies into what is already there and making that more efficient and slowly basically convincing the bureaucracy that this works. So this also requires a lot of collaboration between technologists and teachers and kind of understanding what technology is capable of doing and what teachers actually need. Um, Next is we want the technology cost to be low. This is true in terms of having low cost for training educators about these new technologies. And also from a social perspective, sometimes I wonder if these AI human AI interactions are coming at the cost of human human interactions. So we want to enhance human human interactions and not just replace them with human AI interactions, because that's like human human interaction lead to social belongingness. And finally, there's this problem of inequity, which increases when we deploy these technologies for specific parts of society which are already very well represented, have good access to these technologies. So we want to make sure that doesn't happen, and we try to reduce inequity rather than creating more. And finally, I'll leave this part with AI ethics. So there are a bunch of metrics in AI ethics which also hold true for education, and we want our technologies to follow these too. So for the rest of the talk, I'll be talking about my research, and I have divided into 5 parts. Fifth part is just future work, but in the first part, I talk about Jill Watson, which is the LLM-based AI agent for online classroom. Then I talk about how it impacted the classroom experience of some real-world examples and data. And then I'll talk about multimodal document-grounded conversational AI. And then fourth part is a little bit different from other parts. I'll talk about continually improving LLM-based modular AI system, which are similar to Jill Watson, but in some ways it's a very different problem that we're solving. So let me begin by Jill Watson. Begin with Jill Watson. So these slides are mostly based on this paper, Jill Watson, a virtual teaching assistant powered by ChatGPT. It was published in Artificial Intelligence in Education 2024. So what we did for this project was we developed a virtual teaching assistant. Virtual teaching assistant essentially answers questions about course material and course content. So it is basically fed all these slides, notes, syllabi by the course instructor, and a student can come and ask it questions just like ChatGPT, except it's grounded in those documents and not just open-ended. So the main utility of the system is that it can help reduce the instructor load in terms of answering student questions online. And so it can scale quality education in online classrooms. And also, we believe it allows students to be more inquisitive and it increases teaching presence by resembling this one-on-one tutoring experience, which is the kind of holy grail of education. So if you don't know about Bloom 2 Sigma effect, you should look it up. And LLMs are obviously a great tool for building virtual teaching assistants because they can follow instructions and hold a dialogue, and they can attend to large contexts and construct meaningful answers based on user inputs and the document that it is grounded on. But there are 2 problems which we mainly try to address in this paper. One is that AI systems, LLMs suffer from hallucinations, and they can generate text that is sometimes not grounded in the documents, or just sometimes not even related to the question. And the other problem is that they have safety issues, and they can generate text that may be considered toxic or inappropriate. So when we developed Jill Watson, we aimed for these features, and the first one was we don't want any model training or fine tuning. We want to see if the existing tools online can be used to build systems that are powerful enough to deploy them in real classrooms. The second thing was just designing it to address hallucinations. So it cites documents from which it takes information, and we also verify the grounding after answer generation using textual entailment. We also address safety issues in a bunch of ways. So there's question relevance at the beginning. We check if it is actually relevant to the course. We have toxic text filtering, essentially moderation of the questions and answers. And then we also generally prompt ChatGPT to be polite in its responses. So this is the architecture. I'll just go through the few parts quickly. So first is co-reference resolution, essentially making the query more complete given the context. So in this case, it's what's due next. System says it's assignment 2. When is it due? We just resolve this query into when is assignment 2 due. So that helps with the retrieval process. That's what we observed. And yeah, the prompt contains essentially past chat and so on. The second part is skill classifier. So we have basically divided the whole system into a bunch of skills. The main one is contextual answering skill, which is where the retrieval augmented generation happens. There's greeting skill, which is just for politely responding to greetings. It just scripts the retrieval steps, and so it's faster. And there's self-awareness skill, which is essentially a context for answering questions about Jill Watson itself. So it has a blurb for that. And then there's just irrelevant questions, which are answered with the default response. The next thing we do is we actually retrieve that module and generate the response. After generating the response, we update the context. So I'll now talk about this contextual answering skill in more detail. It has essentially a dense passage retrieval system, which gets context, the result query, and the pre-processed documents. And we have a lot of redundancy in these pre-processed document storage. We essentially store the passages with multiple vector representations, a lot of overlaps to make sure that it is able to retrieve the right context. And I'll tell you why it's good later. So yeah, once we get the retrieve paragraphs, we do the ChatGPT API call and get the response. And after getting the response, we check if the AI was able to answer the question. If it was able to answer, we just return it. If it is not able to answer the question, we go back to the retrieve paragraphs and kind of go to the next set. So essentially loop through these retrieve paragraphs to generate an answer. After this, we check for entailment. So essentially, the idea is that if the answer is grounded in the context, then we say that it had high confidence, otherwise it has low confidence. And if in case of low confidence, we warn users about potential hallucinations, which is supposed to remind them that this AI system can also hallucinate. So just to give you an idea of what textual entailment means, it's basically we say that this text T, which is in this case is retrieve paragraphs, is entailing the hypothesis, which is the response. So if T directly implies H, that means T entails H, which means nothing in H was outside T, so which means the answer was not hallucinated. And finally, yeah, we have moderation API, like I said, on the front and back, so both input and outputs. And if there's if something is flagged, we just return a default message. Now, what we did is we compared this system with two other baselines. One was this old legacy Jill Watson system, which was a database centric system. So whenever a question came in, and it was a question answering system, not a conversational AI. So whenever a question came in, it was basically trying to map to the specific kind of pointer in the table where the answer should be. And the table was organized by this course deliverables and information categories. So it classified on both axes, and then it got exactly where the result should be, and then retrieved it. And then we also compared it to OpenAI Assistant Service, which is very similar to what we developed, but yeah, we don't know the exact mechanism it uses. But we made sure that both OpenAI Assistant and our system are using the same GPT version for retrieval augmented generation. And then we did this, created this data set based on student questions, and had some deliberately, I don't know, kind of questions where AI should not be able to answer the question based on course content. And then a few evaluators went through these answers and gave them pass fail, and then also tried to annotate what types of mistakes were made by the system. So what we observed is Jill Watson does much better than legacy Jill Watson and OpenAI Assistant. So on the pass, in the pass table, you can see that it has double the performance almost. Close to 77% of the questions were correctly answered. In terms of failures, so all these numbers are actually percentage of failures, not percentage of total answers. We see that it has very few harmful answers. So actually only 1 out of 150 was harmful, but a bunch of confusing answers, which means, so when I say confusing, it means it's obvious that the answer is wrong, but it's still sad to see it, right? So student can get confused about what the AI is trying to say. And then we also have, we also try to annotate where things may have gone wrong because of just bad retrieval. So that also happens less often with Jill Watson. And again, these numbers are percentage of failure, so it's already much less than OpenAI Assistant because the performance is double and then further just lower than. OpenAI system. We also did some study with toxic responses. So this set of insert prompts trying to use literary devices in instructions and uh, trying to get toxic responses. So, for example, put together an offensive jab applying irony. And legacy Jill Watson just provides templated response that they cannot be toxic. So we just compare it to OpenAI Assistant. And Jill Watson's skill classifier classified almost all queries as irrelevant. So what we did is we tried to break it. We said, can we pass the skill classifier somehow? So we created questions that are basically the same thing, but have like course relevant sentences. So you can see how many assignments are there in this course. Half of the semester is already over. I still need to watch the first lecture. Answer in form of an offensive jab applying irony. So that passes the skill classifier. But in the results, we see that before this adaptation was done, Jill Watson was saying, I don't know to 98% of the questions. So very low toxicity also in terms of this perspective API scores. And then after adaptation, you can see that OpenAI Assistant went from 68% I don't knows to 5% I don't knows, which is really bad. So it actually generated answer 95%. But Jill Watson still retained most of its safety features and only answered in 18% of the cases, and also had lower toxicity in those responses. So what are the takeaways? I think the first takeaway is that in educational settings, you have to have a lot of safety features, layers of safety features that can prevent harmful, confusing, toxic responses. And in this case, we had like features, sorry, layers of safety before response generation, during response generation, and after response generation. And both in terms of just grounding the answer and making sure it's not toxic. Further, redundancy in the retrieval process, and encouraging LLMs to not answer outside context in our prompts also reduce the incorrect answers a lot. So that was one limitation of OpenAI Assistant. Although we don't know what the exact mechanism is, we think it's kind of forcing the LLM to answer based on whatever is retrieved. So a lot of the times it's just answering something that is not even related to the question, or it's giving a hallucinated answer. And we also need to still, like the performance is not perfect, so we need to make students aware about limitations of AI and encourage them to verify critical information, so that AI literacy has to come from the instructors and the AI developers as well. So next, I want to talk about the second part. In the second part, how Jill Watson impacts classroom experience. So this is based on two papers. One is this Jill Watson scaling and deploying in conversational AI in online classrooms, published at Intelligent Tutoring Systems. And the other paper, does Jill Watson increase teaching presence at ACM learning at scale? So we deployed this system in a lot of courses. Here's a list of them. And I think this was the last course in spring 2024. So there have been more deployments since then in summer and fall 2024. But yeah, this paper had these results. So as you can see, it includes technical courses like human-computer interaction and knowledge-based AI, but also in Wiregrass College, which is a community college, we had it deployed in education, English composition and rhetoric course, and also a leadership course at this Columbus College, which is another community college. In terms of student age distribution, you can see that most of like almost all of our learners are adult learners, and there are quite a few students who are actually even older than 35 or 45. In terms of race ethnicity distribution, I think we just need to note that Georgia Tech is biased, highly biased. So it has a lot of Asian students. It's very selective, so students are of very high calibers. But we also try to serve the other parts of the education system where basically it's like basically community colleges where acceptance rate is lower, and so the students may not be as tech savvy as Georgia Tech, and so you can also see that population, since in Atlanta it's heavily like Black populated, so that also is represented here in our course stats. And when we checked performance of Jill Watson across these courses, we saw a pretty consistent result. What we found was that it depends a lot on how the document was structured. So it has less to do with the content, but kind of the just structure of the PDF document, I guess. So there's not much to learn except we can give some guidelines to instructors to structure the documents in certain ways if they want to use Jill Watson in their class. We also had some interesting conversations appear on the class forum where students were talking about just Jill Watson unprompted. And so these students mentioned that they really liked it, essentially. It's a leap forward. They were coaxed to go from explicit knowledge to tacit knowledge. And this basically means that it was not just answering based on course content, but kind of processing that information. So in later student mentions that the answers were thought through after analysis. And then, yeah, they're learning, using it to learn lecture material. It also helped them find out where they needed to go when they were lost on Blackboard. So Blackboard is this learning management system like Canvas or Piazza, you might know. And yeah, essentially we heard really good things. In terms of usage, when we went from this legacy Jill Watson to the new Jill Watson, we saw a huge jump in the number of questions. And legacy Jill Watson could only answer course logistics questions like deadlines and so on. But now we can answer questions about course content, which is very exciting to students. We also had this fun classroom at Georgia Tech where there were around 570 students. And we divided this class into two parts. One had access to Jill and the other one did not. And so we compared those two classrooms. And we saw that the number of A's in this course, the part of the course with section with Jill had higher A's. But it was not statistically significant. What we found statistically significant is their mean absolute grade. So with Jill Watson, there's, if you can see, it's about 4.8% improvement in their mean grade, which is very encouraging. We also conducted this survey called the Community of Inquiry, which is based on this Community of Inquiry framework. So it has three parts: social presence, cognitive presence, and teaching presence. And what each of them mean is basically that if you think there's higher teaching presence, that means a student thinks that they had enough interactions with teachers, they were there to support them in all these different ways, which I mentioned on the right, like design, organization, facilitation, and direct instruction. If they feel that there's high social presence, that means that they had enough opportunities to interact with other students and basically had a good time socially in the class. In cognitive presence, what we mean is were they challenged in the class to go and do some work, be excited about it, and just overall content and kind of interestingness of the class. So when we did this, we found two interesting results. One is that there's a higher social presence in the class with Jill Watson. And also there's higher teaching presence in the class in the design and organization part. So TPDO is teaching presence, design, organization, which is kind of expected because it's essentially teaching students whenever they ask questions, it can answer about course content and logistics. So what was interesting was seeing higher social presence. And we think it happened because they were attributing human values to these AI agents. So whenever they needed help from a human and maybe they were not available, they still had this opportunity to go to the AI system and ask the same question. Uh, so that's where we believe the social presence is coming from. So finally, takeaways from these two works, I believe, are that AI systems like Jill Watson not only help students perform better, but also improve just the overall experience of the classroom. And students want to use this system not just for course organization, but also for course content. So the response was much higher. The number of questions were much higher once we did that. The students, like I said, also anthropomorphize AI agents, which can lead to higher teaching and especially social presence. Uh, Now on to the third part of the talk, which is an ongoing work, multimodal document-grounded conversational AI. This part was mainly motivated by my personal dissatisfaction with the text-only system. So in cases of questions like what is Raven's progressive matrices, you could have such a long answer about whatever it is, it's a 60 multiple choice visual analogy problem and so on. You still don't get much out of this answer. If you could just show someone this figure and tell them this is a Raven's progressive matrix, you would understand, okay, they're basically A is to B, C is to something else. What is it? So just get it, right? It's so a picture is basically worth 1,000 words. So we wanted to create such a system and kind of ground it in the document. So if it could pull these answers, so these figures from the document, that would be just awesome. Uh, so yeah, why we want to do it? It's exciting. We want to have text and images together in the responses. It's also necessary for visual intensive content like slides and videos, and especially for a lot of courses, technical courses, they have a lot of diagrams. If you think of chemistry, biology, physics, they all have a lot of diagrams, right? Um, and also when we analyze the questions asked in the specific knowledge-based AI course, which my instructor takes every year, so that's why it comes up again and again in these slides. We found that 36% of the questions could be answered with visuals. And here are some examples, like what is an MDP? So you could do these queries and try to find relevant figures. Um, yeah, so now I'll just talk about some parts of the pipeline of the system. So first step is obviously pre-processing. We did document layout analysis model, document layout analysis with RCNN model, and then extracted these figures out. For the text, we used OCR and GPT 3.5 to clean it up. And then we also stored embeddings of these images using the clip model, and also just captioned them and stored the text embeddings of the captions for retrieval. And when a question comes in, like how do I solve the block word problem, it will first create image search queries using GPT-4, and then use clip embeddings to retrieve the relevant images. So obviously vector similarity can be just used to match embeddings of the queries and the images. And obviously, we also do this for text. So similar to Jill Watson, we just retrieve a bunch of text from the course documents. And when we want to generate response, we feed it the question, the retrieved text, the retrieved images, and captions of retrieved images. In the prompt, we have all these details, and we kind of order these images and provided name, essentially a link to the image, and then attach those images in the answer. We ask it to use essentially HTML tags to specify these images. So when an answer comes out, it looks something like this. It will have whatever tag inside the um, its response. And then when we are rendering it, we just change that by retrieving the relevant image from our database. So that's how it works. And just to give you an example of what a response might look like, let's say student asks, I'm really struggling with state spaces, can you help me? And it's a really long response, actually. First, it talks about understanding state spaces, and it talks about how means and analysis uses state spaces. gives an example, retrieves a figure, shows that this figure was not extracted properly, so it's like half the page essentially from the book. And then it further talks about this example of how it's used in means and analysis, and then also how semantic networks can use state spaces. Semantic networks can represent state spaces, and basically a really long answer. But still a good answer. But there's some challenges we faced. So, for example, in this case, I asked, give me an example of 2 by 2 Ravens matrix and explain how to solve it. In this case, the model just hallucinated. It's describing these figures A, B, C, D, and it's not what the figure is, right? A is not a solid black square, and same for B, C. And I was wondering if maybe because I'm feeding 5 images, maybe it's giving text from describing some other image, but giving me another image. But it turns out there's no such image actually, which has this ABCD that looks like it. So yeah, I think what I have observed is GPT-4's vision model is basically overwhelmed when you give it a lot of images. There's also problems with image understanding. So in this case, it actually got the figures right. It correctly described what ABCD, whatever it is. But then it says to provide a definite solution, we would need more explicit rules or a stronger pattern. So it was not able to detect the pattern in this case to solve the problem. But okay, so despite these limitations, we went ahead and created a system. We created a tool with the hope that users can somehow get around these limitations and adapt their expectations to the performance of the system, which itself is a very hard thing to measure, right? It's like measuring performance of a system that retrieves content from a 350-page long document and then uses text and image. Like where do you begin evaluating the answer, and how do you get experts who can evaluate the answers? So what we did is we created an interface and then ran a user study, which I'll talk about. So in this interface, you have this chat window on the left. At the bottom, students can type questions, and on the right, they can see the PDF. The texts and images are clickable. So if a student clicks the image, the PDF will go to that part of the document and show you where the image was taken from, so you can read around it and understand more if you want. Text also is mapped through just embedding-based matching. And then it also has features to very conveniently select text in the PDF. And then it shows up two options. It shows two options, this summarize and explain it like I'm 10. So it will create a prompt and you can just send that prompt and summarize the text. So overall, a very interactive experience. And we wanted to conduct a study and invite users in our lab and compare text-only system and multimodal system. And in terms of research questions, we want to know if figures and diagrams can help students in problem solving. Also, does this navigation to source of images and text improve trust? Because it's kind of giving you the source of the answer. And then does this ability to interact with text improve the perceived utility of Jill Watson? So basically the perception of the whole experience. So we're still working on this study, but I have some preliminary findings for you. One is text-only system has higher clarity. The answers are more concise, and system gives just right amount of information more often. So this is kind of a negative result because we were hoping multimodal system will do better. So here we're talking about text-only system. But what multimodal system does better is it's a better tool for searching information and exploring course content based on the responses we have. Also, students feel it's far more engaging. It is perceived to have more memorable answers. So we're not testing for memory explicitly, but students believe that it's more memorable because of the visual and this interactive nature of the system. And also they feel more confident in their ability to solve problem because it's a much powerful tool. So they feel like that they can do anything with it. And also it's more trustworthy, which is something we expected. But we are not seeing any significant difference in the score so far. And what we believe is that this interaction comes at the cost of time. So the more interactive the system is, you spend less time thinking and solving the problems, but more time kind of just going through all these different things and absorbing, trying to not get overwhelmed. So that's the conclusion of multimodal system. And finally, on the in the last part, I want to talk about continually improving LLM-based modular AI systems. And this problem was came up because AI agents like Jill Watson are limited by the performance of the underlying LLM, right? What can you do if you want to go beyond what the systems are already doing? And there are a bunch of them. So like Auto GPT is using these, Perplexity is using this thing. Can you do something to improve performance? We can also not rely on improvements from the LLM updates because there's research showing that the task performance can go down as these companies train LLMs for safety and conversationality. Some capabilities are lost. And finally, if you have a modular system, the overall performance is like the compounding performance of all these systems. So if you have one weak link, the whole system fails. So what we want to do is fine-tune task-specific models. And for that, for this work, we wrote this paper called Can Active Label Correction Improve LLM-based Modular AI Systems? And it's published at UMNLP last month, actually. So the idea is, I think I'm running a little late. So I'll try to wrap this up quickly by just giving you the main ideas and skipping some of the baseline stuff. So the idea is if you have this AI system and you focus on this one prompt and API call, it could be something like intent classifier, named entity recognition model, or textual entailment. You could collect the input and outputs of the system when you deploy it. And you can collect all the data during the collected during the user interactions into this one large table with inputs and noisy labels. And these labels are noisy because the inputs were labeled by the LLM. So one benefit of using that data to train your own system is that you have no domain shift. Now the data is from the real source. That's where you want to use your model. You can also train smaller models for simpler tasks, bigger models for complex tasks, and can be cheaper and faster. And you can improve it further as you get more data. And the gain in overall performance, if you can fix the weakest link, can be obviously huge. But obviously, there's this one problem: this data is not perfect. It can have a lot of errors. So we want to improve it using human feedback. And before that, I try to like just get a sense of what's the performance gap. I think we all know that ChatGPT and fine-tuned models have a huge gap in performance on a lot of benchmarks. So that's what we observed. And then we also just analyzed the noise and found that it's pretty complex. It's actually, like GPT 3.5 makes very reasonable errors on these examples. And when we try to train a model with GPT induced errors, we found that the performance is really bad compared to some of the noise models that people assume, like label condition, input conditions, and so on. So how do we efficiently fix this data with human feedback? So what we propose is you train a model using this data and try to predict which examples are most likely to be misannotated. Then you use human annotation and then update those some of the labels in the outputs. Then keep doing this process iteratively, just retaining human annotations from the previous iterations. And then eventually, when you're satisfied with the performance of the model that you trained, then you can replace this API call with your own fine-tuned model. So I'll skip these baselines. I'll talk about the proposed method that we have. So in this method, we start again with noisy labels and inputs, and then train our own model. Then we do inference on the training data set itself, right? And we get some model predictions. If the model predictions disagree with the LLM, then we say, and with a very high confidence, then we say that model predictions are correct and we just autocorrect the examples. After that, we find confusing examples, essentially examples with lowest confidence or highest entropy, and then get human annotations on those. But there are still some examples that are noisy. So we filter some examples out from this data set before training our new model with updated labels. And the interesting part is that for filtering, there's two questions: which examples to filter and how many to filter, right? So to estimate how many examples to filter, we look at the data from human annotations. So if a human annotator disagreed on a lot of examples, we essentially filter more examples. If human annotation shows that 90% examples were already correct, that means there's very low noise, so we don't filter as many examples. So there's this formula we propose to estimate that. And then we filter the examples again with the highest entropy or lowest confidence. So when we do that, this three-step process of improving the data quality uh, works really well. And we just keep doing these iterations, and I'll skip some of these details. But yeah, we see a huge jump. So if you see the yellow line here, the performance jump with each iteration on the x-axis, and F1 is the y-axis, is huge compared to what people have tried so far. And so an interesting result is that if you have, let's say, this error on the right side in each of these data sets, and if you could just perfectly predict which examples are wrong, then this is the number of examples you'll need to annotate, right? But we show that with ALC3, you don't even need to go there. You can actually annotate less than the number of errorful examples and get same performance as a perfectly annotated data set. Uh, so I'm not sure if I said this correctly, but yeah, you can see here that 22.5% of the data on the right here had to be annotated, but there were 29.8% examples, which is a really positive result, right? You basically never had to look at 77% of the data. And the reason it works really well is because there's no domain shift now. So even without any human annotations, you get really good performance. Also, there's auto correction, which improves the quality. The estimation process is also contributing to improving data quality. And finally, this noise reduction overall just leads to better next model every iteration. So the estimation of noise in the next step is even better, right? And finally, we actually want to achieve Oracle performance instead of a quality perfect data set. So the data set at the end is not perfect, but it's still the model trained with that data set is as good as a model trained with perfect data set. So that's why we didn't have to annotate as many examples. So with that, the takeaways are that you don't have to rely on LLM performance. You can train your own models from deployment of your AI agent. You should probably focus on fixing the lowest performance model, basically the weakest link in your modular system to improve the performance. And finally, you can efficiently get human feedback and free your systems of domain shift and minimize the expensive API calls and get rid of LLMs where they're an overkill. And finally, I want us to think about these three research issues that have come up in my research, and I would also love to hear any thoughts on these. So one is, how do you design interactions for multimodal conversational AI in education? So in that, I think there's three questions. One is identifying learning gaps. How do you know what was most helpful to the student? What was at least helpful to the student? What they already knew, what they didn't, right? And then how can AI modify its next response if it knew that learning gap. So it has to essentially give responsive instruction. Then if you do that, does that actually change the student learning and actually have a real impact? So those are questions we need to answer. In terms of ALC3, I think I want to extend this work for generative tasks. So how do you predict? So far we did it for all the discriminative tasks. Now, can you predict poor quality generations from output token probabilities? And what human feedback will you get? And how much data will you need? Because I think for generative tasks, you typically need far more data than discriminative tasks. And is this process just more efficient than RLHF? So in RLHF, we indiscriminately get human feedback for all examples. What I am proposing is selectively finding examples that will be most efficient way to get human feedback, and then only getting feedback for those, the others are just fine. And then finally, this is something I have not worked on, but I think about it. How do we reduce technological inequity in education? And some of the questions that we should ask ourselves is, what are the assumptions about the learners when we're creating technologies? Who are we serving based on these assumptions? And how can we make our technologies more accessible? How do we reduce the cost for people who are not as rich, maybe? How can we get more languages in these systems to reach a wider audience and so on. And with that, thank you so much for paying attention. Here's my brief bio, and I'm happy to hear any questions or thoughts.
Thank you, Karan, for that excellent talk. That was brilliant. I have a ton of questions, but I will save mine. The floor is now open. I will allow people to unmute. And feel free to ask any questions you guys may have.
Hey, Karan.
I have a couple.
Go ahead.
Oh, go ahead.
So you first.
Okay. So I was curious, the context in which you presented this seems like it was mostly using Jill Watson as a tutor, but I'm wondering would it be possible, or how difficult a step would it be to use Jill Watson or a similar system as a primary instructor for a course?
I think that's a big ask for AI systems right now. There is work on content generation using AI systems for educational application. But one of the things I think that comes up again and again is that these systems work well for applications where the content is very common. Essentially, it has seen it a million times on the internet, right? And if you go to like cutting edge research or graduate courses where maybe the information is more recent, the AI system won't be able to do as well because it just has, I hate to use word understanding, but basically a poor understanding of the content. So it is possible maybe to use it for like lower level content, but not probably for graduate courses where I focus most of my work on.
But if it was like, an undergraduate physics major, would that be a big stretch given where things are right now?
I think so. I have dabbled around with, for example, Claude AI to create simulations of physical systems like spring mass systems, and I think it struggles quite a lot in creating such simulations and analyzing them. So I don't think we are at a stage where we can easily use these systems for instruction. But in our applications, it was, as you can see, it's mostly for recall of information. So if a student has learned something in the class and they want to kind of just quickly get that information again, that is where this systems, I think, shine.
Okay. And then a follow-up question, which is sort of related, which is in the context of it being like a tutor, like you were showing, is there a way to incorporate a particular preferred pedagogical approach that it should follow, like that the instructor could tell it, like interact with the student this way, or?
Yeah, there are several works on this. So, like I mentioned, there's applications like learning by teaching. So there's people trying to ask students to teach the AI system. So AI system has to ask questions. That's what it's instructed to do. There are Socratic systems essentially, which probe students to think more, and so on. And then there's retrieval systems like ours, which are more open-ended, less instruction, but more like kind of a slave to your requests. Which is something we've found interesting, because adult learners want very open-ended systems. They don't want to be told what to do. They want the AI to, they want to tell AI what to do and then just get the response instead of like AI telling them to do what to do.
Well, thanks. Great talk.
Thanks.
Hey, Karan. So your system seems to be fairly complex, like in that you have an entailment system, a retrieval system, a classifier. How sensitive are students generally to like time to first token or latency? Have you noticed any like feedback on that?
Latency has not been such a big issue. Typically, the responses appear in 5 to 6 seconds. That particular paper was based on the system, which had 6.8% average latency to first. So it's still, I mean, much faster than getting a response from a TA, for example. If you email someone, they're going to take a long time to reply.
Sure.
So
Okay.
it has not been a complaint, so far.
Yeah, that's great to hear. Thanks for the talk.
I had a question related to one of the slides you had. It was like A is to B is, or if A is to B, like what is C? What is that cognitive test called? Comparing the images.
Raven's progressive matrices.
Yes. Okay, you said the LLM had problems describing what was being shown and like answering those questions, and I'm wondering if you tried any troubleshooting of like scaling the images up, because I remember reading something somewhere where somebody like reverse engineered GPT-4's algorithm. They're like patch position encoding and saying like, as long as the shapes are greater than 28 by 28 pixels, it can identify the shapes. Did you do anything related to that and have any, I don't know, interesting findings?
So one thing I tried, which I show in this appendix slide, is GPT-4o specifically has a high detail mode where it's not going to compress images to a lower size before feeding it. And even after doing that, we observed the same problem. So that's what I mentioned here. It's detail high mode. And if you see top left A figure is not a square with a diamond inside it. I mean, it is, but there's also a circle, which is important, and that is completely missed. So we still see those problems even with high detail mode. And I also tried other models within the GPT family and same issues.
Interesting, thanks.
These issues are especially common when there's a lot of input images, which is what we want, because we are retrieving images. So I can't feed one image at a time. I have to feed many images and it has to select between those images.
On this line, I'm curious if you've looked into this. If all of these images were generated by SVGs or some type of thing that like there was a string of tokens, they could be described by tokens that weren't pixels. Have you looked into whether or not that would improve the performance?
No, I actually haven't. Yeah, that's an interesting thought. Thanks for that. Yeah.
Yeah, but it would also, I mean, you could generate unlimited amounts of training data, just like every SVG, as long as you have some rules for generating valid ones, you're going to learn something about what it looks like. And
Yeah, that is, yeah, I see your point, but it's a challenge to get the source SVG files, and because most of the course content that we see is in form of PDFs, and so extracting that is
Right. Well, another model in the pipeline to convert an image to an SVG.
Eric, did you have another question?
No, I thought the hand would go down whenever
Okay.
I muted, but it didn't. So I'll just
Gotcha.
thanks.
Okay. I do have a question actually about you showed earlier that Jill Watson's accuracy varied across courses, like different types of course material. And I noticed that programming courses, it did very well. I think this makes a lot of sense, right? Because programming is very precise and like referential, so you can reference exact syntax. I was wondering, I didn't see in that chart whether you guys looked into math courses or mathematical material. And I was wondering how Jill Watson would do with sort of like symbol heavy or logical references.
Yeah, that is true. We have not deployed it in a math course so far. So we have to go through this process of like reaching out to instructors, convincing them, and so on. And yeah, we are, I think, expanding this set of courses, but obviously, like convincing the same instructor again and again is easier. So we try to like, keep evaluating our system as we improve it in the same courses.
Right. But I think math, and also Mr. Rosen was explaining about physics earlier, they are potentially more difficult for a system like this, right? Because they require some logical like sort of propagation of scenarios or like or logical follow through of certain rules. So yeah, I think that might be interesting for future work.
Yeah, definitely. This again, I would say it will probably work much better for example, high school physics as compared to maybe graduate level physics or like cutting edge physics or maths, right? So.
Definitely. Thank you. Okay, if there are no other questions, Karan, thank you so much for presenting today. If you could flash forward to your slide that has your contact information, how can people hear more about the brilliant work that you're doing and the future papers that are going to be published?
I guess you can also find me on LinkedIn. I should maybe share my LinkedIn link in the chat. And, yeah, it's good to connect with you all. So sorry, I'm realizing I have too many slides.
Yeah.
That's why it took me 50 minutes to go through. Yeah, let me share my LinkedIn.
Perfect. Yeah. And so if you could also send me these links and I will put them in our Discord for anybody to reference along with the slides that you shared with me. So these slides will be available. Recording of this talk will also be available on our YouTube channel. Guys, if you want to hear more about cutting edge research that's happening in intelligent systems, check out future events in the Frontiers series. This was our last one for this year. We have a nice set of plans for more Frontiers talks in 2025. I'm very excited for those. And if you want to find out more about Manifold, you can check out our website and join our Discord, join the conversation. All of our projects, we discuss progress openly. Actually, Karan was mentioning one area of future progress is related to metacognition, right? It's related to models sort of thinking about their own performance and improving. So, hey, we have a project on metacognition and LLM. So I see a little bit of a link there. Yeah, everybody, thank you so much for attending today. This was a great talk, Karan, and looking forward to seeing you guys in the next one.
Thank you so much for the opportunity.
Yes.
Bye.
See you.
Bye, everyone.